In this section, we're going to examine how animals regulate their body temperature. Regulating the body temperature involves adjusting either metabolic processes, an animal's activities, or the animal's environment to adjust the amount of heat entering and leaving the animal so that its thermal energy, and therefore its temperature, does not change. So, what types of animals are we talking about? Well, two major classes of animals are ectotherms and endotherms. Ectotherms are animals that historically would have been called cold-blooded. They are animals whose body temperature is determined by their environment. Endotherms, on the other hand, are animals that can warm their tissues through metabolic processes. We'll be looking mostly at this type, especially those called homeotherms, those who do regulate their body temperature, animals such as mammals. These animals exhibit what's called homeostasis, the tendency of an animal to maintain an internal stability in its physiological system, including its temperature. Our goal for this section is to create a model of a mammal which includes the inputs and outputs of heat to the body. When you add up all the inputs and outputs, you'll determine the change in the body's thermal energy. If you're a mammal, a homeotherm, the inputs and outputs will add up to 0, meaning that your body temperature will remain constant. If something is wrong and they don't add to 0, then the mammal's body temperature will increase or decrease. So first, we need to determine all the processes that can add or take away heat. We're going to consider 5 major ones: metabolism, conduction and convection, radiation from the sun, radiation between the body and the surrounding air, and evaporation. Some of these give heat, some take away heat, and we're going to calculate them and add them all up to determine if there's a change in the animal's thermal energy. Remember that the variable for the amount of heat gained or lost is Q, measured in joules or kilojoules, and that the variable for the rate of heat transport is H, measured in joules per second, or as we'll be using mostly in this section, kilojoules per hour. Since most disciplines deal with rates of heat transport, we'll mostly be writing this relationship as the rate equation. The first process that we'll look at is metabolism, which is the rate at which the body converts chemical energy from digested food or stored fat to useful kinetic and thermal energy. Mammals have what's known as a basal metabolic rate, sort of a base or lowest rate possible. This basal metabolic rate provides the energy for the basic processes of life, such as breathing or pumping blood. Beyond the basal rate, the rate that a body's metabolism will convert stored food energy into kinetic and thermal energy will depend on a few things, including the activity that the animal is engaged in and the animal's size. Animals vary their metabolic rates to provide energy for different levels of activity. In this chart, you'll see listed the rates for different human activities. You can find charts of metabolic rates for different activities online or in textbooks. One of the things that you'll notice here is that the units listed are all per square meter. That's because the metabolic rate also depends on the size of the animal. Larger persons will need larger metabolic rates to provide energy for their activities. Usually, you'll need to multiply this raw metabolic rate by the person's size, specifically their surface area, to get the real metabolic rate for that individual. Humans generally have a surface area that ranges between 1.5 and 2.5 square meters. Here are some other rates for human activities. Remember that these are general or average rates for humans. Humans can and will vary their metabolism based on the activity and other circumstances. Individuals' rate will vary, even between persons of the same size. For this course, we'll use these exact numbers for problems and such, remembering, however, that they are never exact in the real world. Let's take a closer look at where that energy comes from and where it goes. Remember that the body's stored energy ultimately comes from food eaten, and is either directly converted into energy or stored in tissues for later use. The interesting part is where it goes after that. It turns out that only 20% of that energy output is actually used for useful kinetic energy, running, climbing, breathing, etc. The other 80% does not go to useful kinetic energy, but is converted into thermal energy through processes like internal friction. So, for every 10 kilojoules converted from stored food energy, 8 of those go simply towards warming up the body. This explains why your body's temperature increases during physical activity, especially vigorous exercise. So, since we're concerned in this section with how much thermal energy is produced by the process of metabolism, we have to multiply the raw metabolic rate by the size of the person and then just take 80% of it to give us our first input of heat to the body. The next process we're going to take a look at is conduction and convection. You might wonder why we're combining those two. Here's why. You should already understand the process of heat transfer through conduction from the skin to the layer of air right above it. And you should remember that as the air warms, the rate of transfer will slow and eventually stop as the air becomes the same temperature as the skin. If that were the only process involved, we wouldn't be able to lose much thermal energy through conduction because the air would quickly warm up to our temperature. However, you'll also remember from your study of fluids that the warm air will become more buoyant and rise, allowing cooler air to take its place and letting the process of conduction continue. The combination of these two processes, conduction and convection, makes a much more efficient method of transferring heat. So, how can we determine the rate of heat transfer through this process? Well, we start with something that we've seen before, Newton's law of cooling. The rate of heat transfer will depend on the difference in temperature between the skin and the air. Note one interesting thing here. We've talked mostly about cooling the body, but if the air temperature is larger than the skin temperature, then conduction is going the other way, and the body will be gaining heat. So what factors go into that constant out in front this time? Well, there's no layer thickness to pass through, so that's not in here. But the surface area of the person does matter. Now this is the person's exposed surface area. At this point, we'll assume that the clothing that you wear is a perfect insulator and you don't lose heat through it. So only your exposed skin conducts heat. That, of course, is a simplification of our model. Winter clothing manufacturers, among others, definitely have to consider that in their calculations. The variable K sub C is what we call the convective heat transfer coefficient, and is a measure of how efficient whatever fluid surrounds you is at removing heat. That's going to depend on what type of fluid it is and how fast it's moving. Water will conduct heat away faster than air. You'll also lose heat faster on a windy day than on a calm day. Convective heat transfer coefficients have been experimentally determined for a variety of situations. For this course, we're going to stick to the situation of a body exposed to air with a fairly reasonable wind speed. You can use this relationship here to determine it. In it, the velocity of the wind, v, is raised to the 1/2 power and is measured in meters per second. And the units of the coefficient itself are kilojoules per hour meter squared Kelvin. Because there's a lot of material in this section, I'm going to break it up into two parts. For this part, when you come to class, you should be able to explain the difference between an ectotherm and endotherm, or homeotherm, list the processes by which a mammal may exchange heat with the environment, list the factors that affect the metabolic rate of a mammal, use a metabolic rate equation, list the factors affecting the rate of conduction and convection, and finally use the conduction-convection rate equation.